Hello, students. Uh, my name is Ravi Ranjan Kumar, and I welcome you, all of you, to this session of Center of Mass. Okay, we will be covering this topic in one lecture, as many things we can cover. Okay, and the next two sessions will be about collisions, in which we will discuss the principle of conservation of linear momentum and about impulses and about several types of collisions. Okay, in this session, we will focus our discussion on center of mass. Okay, so the thing is, we have already learned the kinematics, dynamics and energetics of a particle. So here, from this chapter, we are going to extend our area, okay, to rigid body dynamics. Like when we want to move from particle dynamics to rigid body dynamics, we generally are looking for a point, the motion of which can represent the motion of a system of particles or a rigid body as a whole. So that is why we have developed one more chapter, okay, which is known as center of mass. Center of mass would be nothing but a point which would be the representation of a complete system of center of mass. So now let's start our discussion. Okay, so here I am going to share my screen with you so that I can write. Okay, so center of mass. So center of mass of a system of particles is defined as, let's say, the position vector of center of mass of a system of particle will be defined as, that would be a summation of, you can say, mi ri upon summation of mi. Okay, so this is the formula which we will be using. Let's say the system has total n particles. Okay, so I will be ranging from 1 to n. I would be ranging from 1 to n. So that is the formula for center of mass of system of particles. Okay, most of the times we generally are using a two particle system, so it is very beneficial for us, okay, to discuss that special case and look closely into that expression. For two particle system, we can say, for two particle system, okay, let's say one particle is m1 over here and m2 is here. Okay, and let's say the distance between these two particles is r. Okay, so the center of mass would be lying somewhere on the line joining them. Okay, somewhere, say here. So this is the center of mass of two particle system. According to this formula, which we have already written, we can find out the value of this R1 and the value of this R2 over here. So the thing is, using this expression over here, what relationship we will be getting is M1 R1 will be equal to M2 R2. Another way of looking at it is nothing but R1 by R2 would be M2 by M1. So this relationship over here gives quite an insight into this formula. This simply suggests that if R1, if M2 is greater, R1 would be greater. Means the idea is heavier the mass, nearer it would be from the center of mass. Okay, or center of mass would be nearer from the heavier body. Okay, so this is one relationship, and obviously in this relationship, this figure we can say that R1 plus R2 is equal to R. So this is equation number 1 and this is equation number 2. So using these two equations, we can very simply say that R1 will be equal to M2 times R divided by M1 plus M2, and R2 will be m1 times r divided by m1 plus m2, and we will be using these two formulas in problem solving quite a lot. So this is the we have defined the position of center of mass of system of particles, and we have specifically developed a formula for two particle system. Okay, so and now what we can do over here, we can find out the position of center of mass for some continuous mass distribution as well. Let's say, for example, this is some continuous mass distribution, and let's take some Cartesian coordinate system. Let's say x, y, z. Okay, so we have developed a formula for center of mass of particle system. Okay, and this continuous mass distribution can be imagined to be made up of small elements which can be treated as particles. So let's say we have chosen one element dm, and its position vector is, say, r. Okay, so the formula for position of center of mass here would be rcom, would be given as r dm, okay, divided by integral of dm, and this integral will be over the whole volume of this continuous mass distribution. In Cartesian coordinate system, x coordinate of center of mass could be written as x dm integral upon dm integral. Similarly, y cum we can write, and similarly z cum we can write. So there is no problem in that. So that is the formula for continuous mass distribution. And another important thing I would like to mention over here, like the symmetricity. When we are to find out the center of mass of a regular symmetric body, okay, so it sometimes it is easier for us. So since we are seeing that the position of center of mass is going to depend upon uh, the mass distribution, okay, so if we can find out some plane of symmetry or line of symmetry or point of symmetry would be even better. If we can find out something, some, for example, let's say line of symmetry. Line of symmetry means around that line the distribution of mass would be symmetrical. So we can definitely say for sure that center of mass is gonna lie somewhere on that line of symmetry. Okay, so center of mass, we can say, uh, of uh, of a mass distribution, will lie on, either you can say, plane of symmetry, if we can find one, or line of symmetry, or point of symmetry. Okay, so that gives us a lot of benefit. Okay, because we can avoid a lot of calculation if we can find out some symmetry in our mass distribution. Like, for example, if we are to find out the center of mass of a uniform sphere or uniform ring, disk, etc., or uniform rod, it is going to be just at the center of all those geometries, and that would be center of mass as long as it is symmetrical distribution. Okay, so now here I would like to put some formulas over here which will be very helpful in solving problems. Okay, and one must remember all those formulas for some given regular bodies. So I will just put it over here. So first of all, if we have a semicircular ring, say, of radius r, okay, so we can say this line over here, this line, let's say this is x-axis and this is y-axis. Okay, so y-axis, you can say that is line of symmetry. In this case, line of symmetry, because the mass distribution right of the line and mass distribution left of the line, you can say, is same, equivalent. Okay, so that is, we can say this body is symmetrical about y-axis. So we can say for sure that center of mass of this semicircular ring is going to lie somewhere on this y-axis. And now see, uh, so center of mass is going to lie somewhere over here. Definitely it is going to be uh, its y coordinate is going to be positive, because the mass is distributed only along the positive quadrant over here. So here, somewhere here, it would be center of mass. We should have a better picture. Apart from remembering the formula only, okay, we must have a better insight into the formula as well. We must be able to guess, we must be able to predict things, okay, before going into the real mathematics or calculation here. So just I'm giving you the formula. So this distance from the center of this semicircular ring, this is going to be 2r by pi. One must remember this formula. And another, if we are having a disk over here, let's say we are having a disk of radius r. This is x-axis, this is y-axis. From the same arguments, we can say the center of mass is going to be over here, somewhere over here. And this distance over here is from center, that would be 4r by 3 pi. Students generally are confused. They remember these formulas generally, that for the formula is 2r by pi or 4r by 3 pi. But sometimes students are confused that they tend to confuse that whether the center of mass in case of disk was 2r by pi, or in case of semicircular ring was 2r by pi. They often get confused even after remembering the formulas. The things get mixed up. Okay, so what insight you can have in this? Okay, see here, the mass distribution in case of the ring, okay, all the mass is distributed from the center of the ring as far as it can. Okay, so definitely the center of mass of a semicircular ring would be away from center, because the mass is distributed, mass is concentrated away from the center. So distance of center of mass will be away from center with respect to that in disk. Okay, so clearly you can say like 2r by pi is greater than 4r by 3 pi. So definitely this 2r by pi formula will belong to this semicircular ring, and this 4r by 3 pi formula will belong to this semicircular disk over here, if one gets confused that which formula belongs to which one. Okay, the next formula I'm going to discuss about is a hollow hemisphere. This is hollow hemisphere. Okay, so this would be the line of symmetry over here. Say its radius is r over here, and its center of mass would be somewhere over here. And this would be, this distance from its center would be r by 2. This is hollow one. And if we have a solid one, say the diagram looks very similar, but let me write solid over here. So if this radius is r, its center of mass would be at distance 4r. Oh, sorry, that would be 3r by 8 over here. That would be 3r by 8. And also you can see here the mass is distributed away from center. So its center of mass is uh, away from away from center, and its center of mass here is nearer to center because of the mass distribution. Similarly, we can have the formula for cone as well. This would be line of symmetry, and all we are interested in case of cone. For example, if the height of this cone is h, so center of mass will be located somewhere on the line of symmetry, and this distance is going to be h by 3 from the base, and obviously from the apex it will become 2h by 3. And similarly this is for hollow cone, and similarly for a solid cone. Okay, that is a solid one. Okay, and its height is say h. So its center of mass is going to be nearer from the base. So this here is h by 4, and this from the apex it is going to be 3h by 4. One can derive these formulas by choosing appropriate element and integrating. Okay, the derivation is quite easy, but uh, even after knowing the derivation, okay, one must remember all those formulas, because in examination hall we don't have much time so that we can derive the formulas. So like we must have those formulas ready with us, okay, in order to be used immediately. So this is the formula for center of mass of some regular bodies, okay. And now one more concept I am going to discuss, that is center of mass of a continuous mass distribution. Continuous mass distribution with a cavity. With a cavity. So the idea, okay, that how can we find out the center of mass if the body has some cavity? Idea behind this, the approach behind this we will be using is simply the region of cavity can be imagined to be a superposition of positive and negative mass densities. So if in a region we have some mass of positive mass density, and although we do not have really some negative mass density, but we can use it for calculation purpose only. Okay, so like if in a region positive, equal and opposite mass densities are overlapped over each other, okay, the thing is like that net mass density will become zero, and that will look like a mass free space, or you can say cavity. Okay, so I'm going to take one simple example, okay, from which we can more clearly see that what I mean to say. Like for example, we have a sphere of radius r. Okay, we have a sphere say of radius r, and we have made a cavity in that sphere. There is a cavity in that sphere. Okay, this is the geometry of this cavity, and its radius is obviously r by 2. Okay, because in the diagram itself you can see that its radius is its diameter is the radius of this larger sphere. So I mean to say, like this sphere has mass distributed all over it. Okay, has mass distributed all over it except the region where there is cavity. So how can we find out the center of mass of this thing? So the idea is to find out the center of mass of this distribution with a cavity, what we can imagine. So let's say we have a in the region of cavity we have positive mass density same as this. Let's say that mass density over here is plus rho. So here also let's imagine there was plus rho, but in the region of cavity only, let me use some other color pen. In the region of cavity only, we have superimposed some negative mass density over here, say minus rho. So only in the region of cavity what we will be having, that net mass density will become plus rho and minus rho, that will effectively give us 0. So this region of cavity will effectively become mass free. Okay, and now we will be having a simply two body system, okay, for which we would like to find out the center of mass. So now let's move ahead with the calculation. So assigning some coordinate, let's imagine this is x-axis and this is y-axis. Okay, and let's try to use our formula which we earlier wrote. So I will draw a column of mass and I will draw a column of x coordinate. We do not need to draw any column of y coordinates, because as we can see that x axis here is acting like a line of symmetry over here. So center of mass is going to lie on somewhere on x-axis. Where on x-axis? On positive x-axis or negative x-axis? Can we say? Yes, definitely. Because see, since there is a cavity in the positive side has got lighter and the negative side has got relatively heavier. So center of mass here would be shifting towards the negative x-axis. Meaning x coordinate is going to be negative over here. So m and x, and we will draw a column of mx. Okay, so the what we can say over here, the since we have assumed that we have a sphere of radius r with mass density rho, and let's say its mass is capital M over here, and it's obviously the center of mass of the larger sphere, x coordinate would be 0, so m times x would be 0 as well. What would be the mass of this smaller sphere of negative mass density? So see, this is the case of volume mass distribution over here, and mass would be directly proportional to volume, and volume is directly proportional to radius cube. So radius is half, so volume will be 1/8, so mass would be 1/8, but also with negative sign, that would be minus m by 8 over here. And its x coordinate of the center of mass of this sphere is r by 2 over here, and their product over here would be minus mr by 16. So now we need to get the sum of this column. So sum of this column would be 7m by 8, and the sum of this column over here would be minus mr by 16. So x coordinate of center of mass will simply be since the formula is summation of mixi divided by summation of mi, means this quantity upon this quantity. So I think that would be minus mr by 16 divided by 7m by 8. So m and m will get cancelled, and we will be getting minus r by 14 over here. So this is how we can find out the center of mass of continuous mass distribution with cavity. Okay, so now uh, move on to discussion of motion of center of mass. Let's try to discuss the motion of center of mass. Let me find the motion of center of mass. Okay, so motion of center of mass, so we have already found out the formula for the position of center of mass, and using the same formula we can find out, we can differentiate it both sides in order to get the formula for velocity of center of mass. So velocity of center of mass will be given by summation of mi vi upon summation of mi over here. Okay, and rearranging this formula, also we can say that summation of mi vi will be a total summation of mi times velocity of center of mass. Okay, so that gives us the left hand side is clearly summation of mivi is the net linear momentum of the system. Okay, and that would be the total mass of the system times velocity of center of mass. And this here is a very, very important formula. Apart from the formula which we derived for velocity of center of mass, this is the expression for velocity of center of mass. And this enables us to find out the linear momentum system of particles, no matter how complicated its motion is. So if we can identify the center of mass and look at its velocity, we will be very well in position of telling that what would be the linear momentum of the whole system. So that is very, very, very important relationship over here, and we are going to use this formula a lot in the discussion of the dynamics of rigid body. Okay, and similarly we can have a formula for acceleration of center of mass. Acceleration of center of mass, again this relationship we can derive by differentiating the above relationship, this relationship over here, with respect to t both side, and we will be getting summation of miai divided by summation of mi. And this formula again, this formula over here again, by rearranging we can find out one another important relationship, and this says that summation of miai would be equal to summation of mi multiplied with acceleration of center of mass over here. And for example, this left hand side we can say like miai term, like miai would be nothing but force on ith particle. Okay, that would be simply force on ith particle and summation of it, and that would be total mass of the system multiplied with acceleration of center of mass. Okay, and now let's look more closely on this relationship over here. So net force on the ith particle will be comprised of, okay, the force, the external force acting on the ith particle, means that is from outside the system, and internal force that is acting on the ith particle from inside the system. Okay, like the net force on ith particle will comprise of external as well as internal forces from the system, and that will be equal to mass times acceleration of center of mass. So this simply gives us summation of f external on ith particle plus summation of f internal on ith particle, and that would be mass of acceleration of mass times acceleration of center of mass. Now closely looking at this term over here, what we can say, this term will sum up to equal to 0, because the forces which are internal to the system, inside the system, will always appear in pair, and internal forces will be action reaction pair, so equal and opposites, they will cancel each other. So summation of internal force would be equal to 0. So here we have derived a very, very important relationship that says the external force, or f external force, okay, or simply we can say net external force on the system is equal to total mass of the system into acceleration of center of mass. So this here is a very, very, very important relationship, because when we discuss the dynamics of rigid body, like the motion of the rigid body might be very, very complicated, and if we are somehow looking for, like, if net external force we can find out, so acceleration of center of mass definitely we will be able to tell. And if somehow looking at the kinematics of the situation, if we somehow know the acceleration of center of mass only, okay, we are not interested, we might not be interested in the acceleration of other points inside the system, but only if we somehow know the acceleration of center of mass of the system, we will be able to tell that what is the net external force acting on the system, and that will be really helpful. We will see that in some of the examples later on. Okay, so after this discussion, let's have a few problems over here related to motion of center of mass. So this here is a problem diagram, all you can see. Okay, so what we are having is, let's read the question, a sphere of mass m. So what we are having is this sphere of mass m and radius r is held on a inner wall of a hollow sphere. So this larger sphere is a hollow sphere, and this smaller sphere is held on the inner wall like this. The orientation is given to us. Okay, and the hollow sphere has mass 4m and radius 6r, that is shown in the figure as well. Now the bigger sphere is kept on a smooth horizontal table. So this table over here is a smooth. Okay, and the center of mass of the sphere lies on a horizontal line. So this center and this center lies on a, means this line here is horizontal line. This is a horizontal line. The system of the sphere is released from this position. The smaller sphere slides on the inner smooth wall. So this will slide from here to here. Okay, smooth wall to reach the other extreme position. The other extreme position I have shown using the dotted line. What would be the displacement of larger sphere? So we have to find out the displacement of larger sphere over here. So we can see how we can move ahead in this question is very simple. See, this system of the large sphere and smaller sphere, if we consider the external force acting on this system, we can see that there is the horizontal force acting on this system will be equal to 0, because this surface is smooth. So so friction will not act. So net horizontal external force on this system is going to be 0, although there would be internal force which may be horizontal at instances, but we are not really worried about the internal forces of the system. We are only interested in external forces of the system. So external horizontal force is definitely 0. So that is not gonna cause any acceleration of center of mass along the horizontal direction. So along the horizontal direction, acceleration of center of mass is equal to 0. So velocity of center of mass will be equal to 0. Now you have to see that both the bodies will be moving. Okay, but effectively the velocity of center of mass will be 0. So center of mass will be at rest. So displacement of center of mass is gonna be equal to 0. So in order to have that thing, like for example, if this smaller sphere is going left, so in order to keep the center of mass's position unchanged, the larger sphere has to move right of it in order to keep the position of center of mass unchanged. Okay, so how are we going to find out the displacement of the larger sphere? So for example, let's say let's name it, the larger sphere says body number 1, and the smaller sphere is, let's say, body number 2. Now you can see the initial position of this smaller sphere is here, and the final position of the smaller sphere is here, but the larger sphere itself would be moving. So one thing we can definitely say for sure, like this thing would be the displacement of the smaller sphere with respect to the larger sphere. Okay, although the larger sphere is moving, it is very clear for us to see that the displacement of the smaller sphere with respect to larger sphere would be this one. So this distance from here to here is 5r, and this would be 5r as well. So this is gonna be 10r. So what we will be writing is like displacement of 2 with respect to 1 uh, and let's take this direction as positive. So the displacement here of 2 with respect to 1 is negative, so that's we can write minus 10r. Okay, and now let's say the displacement, that sphere would let's say move by 1, so displacement of 1 let's say is x. So from that we can find out the displacement of the body 2 with respect to ground, the displacement of smaller sphere with respect to ground, and that would be simply s1 plus s21. Okay, using the equation, so x minus 10r would be the displacement of 2. So since we have said like delta x com is gonna be equal to 0, so what we can say that m1 delta x1, or simply let's say s1 m1 s1 plus m2 s2 is gonna be equal to 0. So m1 is 4m and s1 is x and m2 is m and s2 is x minus 10r over here is equal to 0. So this relationship gives us that x will be equal to, I think that would be 2r over here. So that would be our answer for this part of the question. So now let's move on to some other question over here. So now what we are having in this question, we are having a uniform thin rod of length L standing vertically on a smooth table. So at the same time, let's begin to draw the diagram also. So let's say we have some smooth table and a uniform thin rod here of length L. The length of this rod is L and standing vertically on smooth table. And consider the lower end of the rod as origin. So let's assign the coordinate system. So this x-axis and this is y-axis. So this here is origin. Okay, and it is also written vertically up, given the lower end of the rod as origin and vertically upward as the positive y direction. A slight disturbance causes the lower end to slip, okay, on the smooth horizontal table along positive x direction. So a slight disturbance will make it slide in the along the positive x-axis, and the rod begins to fall. So what is being asked to us in the part 1 of the question is, what is the path of center of mass of rod during the fall? So initially, the center of mass would be somewhere here at the center of this rod, center of this uniform rod, we must say. So center of mass would be here at middle. So that is L by 2 distance from both the ends. So here it is the center of mass. Now looking at the dynamics of this problem over here, what we can say, see this surface is smooth. This surface is smooth, so the friction is not acting on this rod. So the only force that is acting on this rod is either gravity and normal over here. So both these forces are acting in the vertical direction only. So the acceleration of center of mass is only along the vertical direction, and obviously it is vertically downward. Okay, so although the motion of this other points of the rod would be complicated, but the motion of the center of mass of the rod would be really easy to predict, since it is a center of mass is only accelerating vertically downward. It will move in this direction only, although other particles will move in some complicated direction, but the motion of center of mass would be only in vertically downward direction. So let's say at any instant the center of mass comes here. So at that instant, and center of mass is anyway going to be at the center of rod, so at that instant the orientation of rod would be somewhere, some somewhat like this. Okay, so this is the center of mass over here, and at this instant say theta. So the answer for the first part, the path of center of rod during the fall would be a straight line, and that will move in vertically downward direction. Now another interesting question that has been asked to us: what is the path, sorry, second part is write the equation of path followed by a point P on the rod which is at distance R from the lower end of the rod, and R is also we must not say not equal to L by 2, that is R should be less than L by 2, we must write. So let me use some other color pen. So this here is the point P which we are looking for, and this distance is given to us as R, and we want to find out the equation of path of this point P over here. So I think it is very easy for us to find out. So see, so definitely this height would be its y coordinate, and this here would be its x coordinate. And looking into the geometry of this triangle over here, y definitely we can say that would be equal to r sine theta. And looking at the geometry of this triangle over here, this base would be x and this angle here is theta. So this hypotenuse is nothing but L by 2 minus R. So x we can write it as L by 2 minus R cos theta. So that is equation number 1, and that is equation number 2. And solving these equation, eliminating theta, we will be getting x square divided by L by 2 minus R whole square plus y square by r square is equal to 1, which is equation of ellipse. Okay, that is equation of ellipse if r is not equal to L by 4. Okay, and it will turn out to be the equation of circle if r is equal to L by 4, because see, then this quantity and this quantity over here will become same, so that will represent a circle then. So the equation of the point P, the trajectory of point P, will be either ellipse or a circle depending upon the value of r. So this is the question which we learned. And now let's look at one more question for the motion of center of mass. So what we are having over here is this diagram over here. Let's try to read into the question. So that is a point like ball of mass m. This is a ball of mass m is tied to the end of a light string which is attached to the top of a vertical massless rod. The rod is fixed to a block of mass capital M lying at rest on a horizontal surface. This is the block M which is lying at rest at a horizontal surface. The pendulum is displaced to a horizontal position, as we all can see, with a string just taut and released. And friction, this time friction is there. So friction between the block and horizontal means over here. And horizontal surface is large enough to prevent the block from sliding. So here this block capital M is not sliding over the horizontal surface. Find the friction on the block when the string makes 60 degree with the vertical. So let's move on to this question. So we are looking at the instant when this would be making 60 degree from the vertical, as when we will release, this particle will go on a circular path. Okay, and at some instant it would be here and over here. So the approach we are looking for over here, what we are trying to find out, since this block is not moving, so the acceleration of block capital M is 0. But as the motion goes on, obviously this particle of mass m will certainly have some acceleration. So once we are able to find out the acceleration of this particle, okay, of mass m, Okay, then we will be able to find out the acceleration of center of mass. Okay, so acceleration of center of mass, and since we are looking for the frictional force, and friction on this block is going to act along the horizontal direction, we will be looking for the horizontal component of acceleration of center of mass, and the only external force in horizontal direction, that would be friction. So friction would be total mass of the system times acceleration of center of mass along the horizontal direction. So that is our intent, that is our approach to solve this question. So let's begin. Okay, so when the mass m would be reaching over here, it will attain some velocity v. Okay, and this v, using work using conservation of energy, we very well we can find out that would be equal to root gl, because this angle theta is given. So over here, let me use some other color pen. So over here, the forces acting on this would be mg, and this is going to be or rather, let's not use forces over it. Simply we can say, since we know the velocity over here, we can simply say that this acceleration, the tangential acceleration, is going to be g sine theta. So that is simply going to be g by 2. And this centripetal acceleration, this is circular motion, that is why we are able to do it so easily. So tangential acceleration is g sine theta, that is g by 2, and the tangential acceleration would be nothing but v square by L. The tangential acceleration would be v square by L, and when we will be using this value of v, this centripetal acceleration over here would be simply g. This is tangential acceleration, and this is centripetal acceleration. So now let's say, let's redraw the diagram over here. So this is g by 2 in this direction, in the tangential direction, and in the centripetal direction, let's say this is g over here. And let's resolve all these acceleration in mutually perpendicular direction along x and y axis. So this angle here is given to us as 60 degree. So this angle here would be 60 degree as well. So let's resolve them now. So when we will be resolving this g over here, so this would be g cos 60 degree, that would be g by 2, and this would be g sine 60 degree, so that would be root 3 by 2g. So we have already resolved this, and the another one, when we will be resolving this, so this is g by 2, and g by 2 cos 60 degree would be giving us I think have we made some mistake? This is 60, 30 and 60 degree. So this direction here, so that is g by 2 cos 60 degree would be simply, I think, g by 4, and this is g by 2 sine 60 degree. I think I have made some mistake over here. Sorry. This is g by, this is g, this is g sine, sorry, tangential acceleration would be g sine theta, and sine theta is going to be root 3 by 2g. So this component is root 3 g by 2 over here. So what we can say, like g cos 60 degree, that would be root 3 g by 4. So what we can say, the acceleration overall, we can write over here, this component will become 3 root 3 g by 4 over here, and this component here root 3 by 2. So this is 3g by 4 over here. So this would be g by 4 over here. So we are only interested in this component, I guess. Okay, so what we can say, that acceleration of center of mass now we have to calculate. So mass, that is the formula is summation of MIAI divided by summation of MI. So MIAI, that would be capital M into acceleration of this a small m over here, or small m, let's write over here, m into what we can say, acceleration is 3 root 3 g by 4 over here, and that divided by the total mass of the system, that is m plus m. And the friction which would be acting in this direction, that would be F, will be total mass of the system, that is capital M plus m, into this acceleration of center of mass, that would be m into 3 root 3 g by 4 divided by capital M plus m. So this thing will get cancelled, and this would be the magnitude of frictional force. Okay, so this was the problem I wanted to discuss, and we have still 10 minutes left. So one more important aspect of this part of topic I want to discuss, there is something called C frame. Okay, center of mass frame. And if we discuss many problems using the concept of frame of center of mass, it is very beneficial. So let's try to discuss about the C frame. So C frame, we have learned how to find out the position of center of mass, velocity of center of mass, and other things. So if we are analyzing the motion of different particles of the system from within the center of mass frame, center of mass frame means the observer will be having same velocity, same acceleration as the center of mass of the system. So in C frame, before proceeding, the first thing we would be looking to learn over here is you can say the linear momentum of system in C frame, and mostly we will be restricting our discussion to a two particle system. So let's say we have a two particle system of mass m1 and mass m2, and this particle is moving with some velocity v1, and this particle is moving with some velocity v2. Okay, so here can we write the velocity of particle 1, okay, with respect to center of mass? So that is very easy for us. So that would be simply v1 minus vc over here, and we know the formula for velocity of center of mass. So that is simply m1 v1 plus m2 v2 divided by m1 plus m2. And rearranging this expression over here, v1c we will be getting is m2 times v1 minus v2 divided by m1 plus m2. So similarly, what we can say, that the velocity of 2 with respect to center of mass, looking at the symmetry of this relationship, that will turn out to be m1 times v2 minus v1 upon m1 plus m2. Okay, so now let's try to find out the linear momentum of particle 1 with respect to center of mass. So that is definitely going to be mass of particle 1 multiplied with the velocity of 1 with respect to center of mass, which we have already found out over here. So this will give us m1 m2 divided by m1 plus m2 into v1 minus v2 over here. And this term, this m1 minus m2, this m1 m2 divided by m1 plus m2 is known as reduced mass. So, and its symbol is mu. So mu times v1 minus v2 we can say. And similarly, when we will be calculating linear momentum of 2 with respect to c, we will be getting mu times v2 minus v1 over here. Okay. So the things to notice over here, first of all, we can see that P1C, linear momentum of 1 with respect to C, is equal and opposite of linear momentum of 2 with respect to C. And the another thing you should notice, the magnitude over here, P1C's magnitude is same as P2C magnitude. And in simple language, simply we can write that would be mu times V relative. Okay, V relative is basically uh, the relative velocity of either 2 with respect to 1 or 1 with respect to 2, v2 minus v1 or v1 minus v2. Okay, and this also enables us, if we want to find out the linear momentum of the whole system. Okay, so this is going to be p1c plus P2C, okay, and that is with respect to center of mass. We are finding out linear momentum of this whole system, and since we are having this relationship, this will turn out to be equal to 0. So these all relationship about the linear momentum of the particles and the system as a whole, okay, in C frame are very important for problem solving. We will be looking in next classes, okay, when we will be discussing collision and all. This will be very important for us. The next thing I would like to discuss is the kinetic energy of system in C frame, like kinetic energy of system of particles in C frame. Okay, so the kinetic energy in C frame, we will be using this symbol generally, that is K tilde. Okay, so that would be kinetic energy of 1 with respect to center of mass plus kinetic energy of 2 with respect to center of mass. And since we already know this formula for the linear momentum, and K is equal to P square by 2m formula we already know. So here what we can say, that would be simply um, uh, P1C square by 2m1 plus P2C square by 2m2. Okay, so like what we can say, solving this relationship, what we will be getting is half mu v relative square, and that is a very important formula. K tilde is equal to half times mu v relative square. That is very important formula. Again, let me tell you, like mu is nothing but the reduced mass, that is m1 m2 divided by m1 plus m2 over here. And the another thing, if we know the kinetic energy of system of particle in C frame, that can also be termed as internal kinetic energy. So from this relationship, if we know this value over here somehow, okay, so kinetic energy of system in ground frame also we can tell. In ground frame we can tell. So in ground frame, simply kinetic energy would be nothing but a half m1 uh, v1, or simply half summation of, you can say, mi vi square. This term we can use. And see vi here in terms of velocity of ith particle with respect to center of mass plus velocity of center of mass, we can write. So when we will be using this expression over here, I'm not going to derive that, I'm simply going to write the final expression over here. It will turn out to be the internal kinetic energy, that is kinetic energy with respect to center of mass plus half total mass of the system times velocity of center of mass square. So this formula is also very important. So that says that the total kinetic energy of the system in ground frame will be the equal to internal kinetic energy of the system, that is the kinetic energy of the system with respect to center of mass frame, plus we can consider this term belongs to the motion of a center of mass as a whole, because m, capital M here is the total mass of the system, and VCOM is the velocity of center of mass system. So this term over here is by trying to consider like the motion of center of mass, like whole body is concentrated in, at center of mass, and it is moving with velocity VCOM. So that effectively will give us the total kinetic energy of the system. And let's very quickly try to solve one simple question. One simple question I have, that is this problem I have taken from the Irodo book, and that is very simple one. So that says the two small disks of mass m1 and m2 interconnected by a weightless spring rest on a smooth horizontal surface. So we have two disks and of mass m1 and mass m2, and they are connected by a massless spring over here, and that is placed on a smooth horizontal surface, and the disks are set into motion with initial velocity v1 and v2 whose directions are mutually perpendicular. So let's say v1 is in this direction and v2 is in this direction. They are in mutually perpendicular direction, and we are required to find the total energy E, okay, E tilde of this system in the frame of center of mass. So internal kinetic energy is being asked to us, and we need not do any calculation because we have already derived an expression for that. And so that becomes a simple formula based question, and that would be half mu v relative square. So that would be equal to half, and mu is definitely going to be m1 m2 divided by m1 plus m2, and v relative in this case, since the angle between v1 and v2 is 90 degrees, so v relative is going to be root under v1 square plus v2 square, and definitely its square would be simple v1 square plus v2 square, and that would be your answer. Okay, so this is a little bit about center of mass and its motion, and in the next lectures, let me get back to webcam, stop sharing so can okay. So here in today's lecture we discussed about how to find out the position of center of mass and velocity of center of mass and acceleration of center of mass, and looking at those values, how we can predict the dynamics of motion of a system of particles. Okay, and we particularly looked at the motion of system of particles in center of mass frame also. Okay, so the next two lectures will be about a conservation of linear momentum, and about we will learn about impulses, and we will learn about collisions in the next two lectures. Okay, so here let me conclude this session. Okay, let me end this session, and thank you very